Okay, so we're going to be looking at forces and motion chapter, and then specifically within that chapter, forces as vectors. So we're going to start looking at how we can use vectors to describe the way in which forces act, and how we can combine forces in the same way that we combine vectors. And effectively, by representing forces as vectors, we can do the same sorts of manipulations as we do with vectors. We can apply those likewise to forces. Okay, so what I first want to talk about then is visualizing the resultant forces. Now, we've talked a little bit about this before, but let's say I take an object, in this case some sort of box, for instance, okay, and I'm going to then say there's a couple of forces acting on it, or let's say three forces. So I've got one force acting this way. Okay, I'm not going to say where it's coming from, but it's acting on the box in this way. Let's say perhaps I've got another one like this. Maybe there's a third force like this. Okay, so we've got three forces, and for any object, you've got all these forces acting on it. We can define a resultant force, and the resultant force is going to effectively be the sum of all the forces that are acting on this object. And sum we use literally as in the addition of the vectors representing these three forces, right? So if I let's just move through the cross. If I can just sneakily create a copy of this, okay, so what I'm interested in is the arrows. Can I just get rid of this? Oh, there we go. Hang on. Okay, so I mainly just want the red arrows in this picture, right? So if I stick them together head to tail, I'm going to get a sort of gap. Okay, and then the gap that remains, that's going to be, remember they've got to be head to tail. This is now my resultant force. Okay, that's my resultant. Okay, and what's interesting about this is that it doesn't actually matter what order you put these arrows in, right? So again, let's just stick this over here. If I make a copy of this one, so let's say I take this arrow first, this one. Oh, can I grab it by itself? Come on. There we go. So let's just take that arrow, and then let's stick this arrow at the end of it, and then let's take the little red one here. Okay, as long as they're head to tail, it doesn't matter. Okay, the order of addition doesn't matter, right? As long as you're adding them up in the so that it's head to tail, and then you can see that in fact the resultant's still the same, right? The missing gap between the two, that is in fact still the same. You've got the same resultant there. Okay, so geometrically, this is what you can kind of imagine. It's like taking all of the forces acting on an object here, putting them in together in some order, and whatever's left, that is the resultant. Okay, and the order again doesn't particularly matter. So that's the geometrical interpretation of resultant force. Then the next thing to talk about is resultant forces and equilibrium. So equilibrium, right, we should note this clearly. Equilibrium means the resultant force is zero. Okay. Now, remember that the force, in some sense, is a vector, right? So when we say a vector is zero, then we're effectively saying all components of the vector are zero. So, for example, e.g. in 2D, the resultant force is equal to and then we can say a two-dimensional column vector 0, 0, which of course is the same thing as 0i plus 0j. Okay, so if you're finding the resultant force of an object and you get 0, or you get the 0, 0 vector, then that tells you that it's in equilibrium, and equilibrium just means that effectively it's not speeding up or it's not slowing down. Okay, so that's what we mean by equilibrium. The resultant force is 0. In terms of the diagram, let's just draw another one of those boxes again actually. So if I have a box, okay, and again let's draw some vectors on it. So I'm going to try and force it a little bit now. Okay, well actually let's do a simpler case. So I've got two vectors, right? Okay, so now with those two vectors, if we assume that I've drawn both of those arrows to be the same size, you could imagine that this object is going to be in equilibrium, right? The forces are pushing and pulling opposite to each other, is in equilibrium. And then if you were to actually, put the arrows end to end, so I say I take my first arrow, and then I take my second arrow, right? And now in this case, they kind of, go over the top of each other. But you can see that effectively the resultant force is going to be 0 because you end up back where you started, right? It's a bit unclear when it's just two vectors. So let's just briefly try it with 3 as well then. So let's, again, I need to try and force this a little bit, but okay, let's say I've got that. Well, actually, this would be a nice example of figuring out what the third force should be if this were to be in equilibrium. So let's say, for example, you're looking at this image and you've been asked to add a third force. So you've got two forces, add a third one so that the object's in equilibrium. If you wanted to do that, this is how you would do it, right? You would take, this is just geometrically now, obviously, and if you haven't been given any numbers. Take those arrows, okay, and then let's find the resultant here. If that were it, it's a bit approximate, but there we go. And now if I place that, if I place that and say that's my third force on the object, okay. So forget the fact that two of them are red and one of them's blue. It doesn't particularly matter. Let's say these are the three forces acting on the object. Now the object is in fact in equilibrium, because if I add up that vector, and that one, I end up where I started. It's like I've not moved at all. So it's a 0, 0 vector as the resultant. Okay, hopefully that makes sense. So let's look at the first of our examples. This one's pretty simple, to be honest. Almost too easy. Let's just quickly blast through it though. So we've got 4 forces in this example, right? Only one of them you've not been given numbers for, and you've been asked to find the values of A and B. Well, the additional information you have as well, of course, is that the object is in equilibrium, right? It's in equilibrium, so therefore we know that the resultant of all the forces is going to be 0. So effectively you're going to form the following equation, right? You're going to say the 2, 3 vector plus the 4, minus 1 vector plus the minus 3, 2 vector plus A and B is equal to, and it's in equilibrium, so we know the resultant is 0, right? The addition of all the vectors is therefore 0. And then from this you're just going to get some sort of very simple equations, aren't you? So you'll get 6 minus 3 plus A, so we can hopefully see that in that case A is going to be minus 3, and B, if I add up the bottom here, I'll get 3 minus 1 is 2 plus 2 is 4, 4 plus B is 0, therefore B must be minus 4. Okay, and I've used column vectors in this case. Again, I personally prefer column vectors to using I's and J's. You could technically write this whole thing out using I's and J's, but yeah, that's a personal preference, in which case you'd have to, for the 0, 0 vector, you'd have to call it 0i plus 0j. Okay. Now in this example, you're going to have to do a little bit extra. Again, it's partly a recap really of stuff we've done before, but let's just remind ourselves a little bit. So part A, we're finding the resultant force in this form. All that's stating is that whatever you end up doing, whether you use column vectors, IJ notation, make sure that at the end you are in fact writing it in IJ notation. But all your working can be in column vectors if you prefer it to be. In my case, I do prefer that. So we've got three forces. Let's write those down. So we've got 2, 1, and we've also got 3, minus 2, and minus 1, 4. Add all that up, and we get 4, 1 minus 2 minus 1 plus 4 is 3, and then we're going to say that is in fact 4i plus 3j. And you don't have to specifically say p equals 4, q equals 3. As long as you've written it in the form they've specified, that's fine. Okay, so that's A done. So then let's look at part B. So we need to work out the magnitude and bearing of the resultant force. Magnitude is very, very easy. All we have to do is use our absolute value symbol or magnitude notation. So that's the two straight lines on either side of the vector. This indicates I'm looking for the magnitude, and this is, just by Pythagoras, equal to the square root of the squares of the components added together. So that's 4 squared plus 3 squared, and you can recognize that straight away as hopefully root 25, and that's equal to 5. Okay, and for the bearing, you just have to draw yourself a triangle really. So let's draw the triangle of the force. Okay, so the force is the hypotenuse, and we're going 4 horizontally, we're going 3 upwards vertically. And if it's a bearing in that sense, so we've got to be a bit careful when it says the angle of the vector and the bearing of a vector. I suppose in the case of a bearing, what we're going to have to do is find the following. You want to find the angle, let's rub that out. You want to find the angle as compared to north. So you're going to have to draw yourself the north line and then say, well, that's the thing I'm interested in, isn't it? That theta there. So if we perhaps then just label this one here something else, let's say phi. Okay, so then phi is going to be equal to tan inverse opposite over adjacent, in this case 3 over 4. Okay, and tan inverse of 3 over 4 should give us about 36.9 degrees approximately, and therefore based on the diagram we know theta is going to be 90 minus that, isn't it? 90 minus the phi, so 90 minus 36.9, that gives us 53.1 degrees. Okay, and that's B done there. Finally, for C then, describe the motion of the particle. Not a particularly exciting question, but just in case that kind of thing is asked, you just have to say, what is it doing? Is it standing still? Is it accelerating? And in which direction? To be honest, this is it's a little bit too basic really, but let's just make sure we know how to answer this. So, describe the motion of the particle. We're going to say acceleration in the direction of the resultant force. Okay, so that's a bearing of 53.1 degrees. And I suppose you could potentially also then mention the magnitude of the acceleration. No, that'll come later. So for now, you can just say it accelerates. Okay, if there's a resultant force acting on an object, it accelerates. If there's no resultant force, it's in equilibrium, then it does not accelerate. Okay. Right, so let's have a look at some questions. What I'll ask you to do is just pause the video, and once you've paused it, have a go at the question. When you think you've got the answer, just unpause it, and we'll take a look at the answer. So have a go at the question, pause the video now. Okay, so pretty self-explanatory, this one, I think. Shouldn't be too bad. Should have gotten this as your answer. A equals 3 and B equals 4. Okay, a bit different this one, in that you're going to have to do a little bit of simultaneous equations. Give it a go, pause the video. Okay, and then this should be your answer here. A is 3, B is 1. Okay, and then now in this question, you're going to want to find the resultant force and then double check you're able to find the magnitude and the angle of the vector appropriately. Be careful that you're reading carefully part C, because you want to find the angle between the line of action of R and the vector J. Right, so remember J is the vertical. So pause the video now, give this one a go. Okay, and there's your answer. P is 2, Q is -6. Root 40, that should be your magnitude, and the angle was 18. Then penultimate question here. Similar to the previous one, but you're going to have to do a little bit of extra work in now finding what happens when you remove a force. So give that one a go. Pause the video now. And there's your answers. Okay, and then final question for you here. I'm not going to give you any tips on this one. Just see if you can give it a go. Pause the video now. Okay, and there's your answer to the challenge question.